Hello and welcome to this video in which I'm going to do a comprehensive review of circuits. As you probably know, circuits is one of the big 5 topics on the FE Electrical and Computer exam. Circuits also has an outsized influence on the FE Electrical and Computer exam because first of all, it's a heavy hitter, and secondly, it also shows up in different ways, forms, and shapes in the other sections such as electronics, power systems, linear systems, and even in the PE power exam. I conducted this interview with students who are enrolled in my FE Electrical and Computer live training program, and in the full session, we went through all the components in detail. The live training program builds on the on-demand content which contains 250 plus lectures, 100 plus quizzes, mini exams, computer simulated practice exams. Before we dive into the content, I would really appreciate if you could like this video and subscribe to the channel if you haven't already done so. And also feel free to check out my website www.studyforfe.com if you're preparing for FE Electrical or PE Power exams. So let me do a quick strategic review of circuit analysis. Whether you are starting circuit analysis from scratch or you have completed this entire section, these are some of the key topics that you need to have a good handle on. It all starts with fundamentally Ohm's law, okay? And then that sort of evolves into KCL and KVL. As far as the KCL is concerned, it is the law of conservation of charge, and KVL is the law of conservation of energy, basically. And law of conservation of charge is law of conservation of matter, and KVL is law of conservation of energy, okay? When it comes to KCL and KVL, one of the most important things that you have to remember, I'm going to quickly sketch batteries, right, is that whenever current is entering the positive terminal of a voltage source, it's considered to be a voltage drop. Whenever the current is leaving the positive terminal of a voltage source, it is considered to be a voltage gain. Whenever current is flowing through an impedance, okay, for our practical purposes, you know, in the context of FE, electrical, it's really resistors, but let's just call it impedance, there will always be a voltage drop. Trust me, if you understand this fundamental conceptual piece of knowledge, it will prevent you and save you from making a lot of mistakes. Is that clear, guys? All right. Identify nodes clearly. Node is created whenever you have a circuit element in between. Okay. So this will be a VA and VB if current is flowing between VA and VB, regardless of the direction. And if you have a resistor, if you have a capacitor, if you have an inductor, if you have a voltage source, if you have a current source, okay, dependent, independent, whenever you have circuit elements in between two nodes and current is flowing through them, these voltages are not the same. And they are considered unique nodes, okay? Now, for two resistors to be in series, same current must be flowing through it, okay? For two resistors to be in parallel, they should have identical nodes. The nodes have to be shared like this, okay? So this is a series parallel. Superposition, although it's not explicitly mentioned in the reference handbook or in the exam specification, it is a very handy technique when you have less than 3 power sources, okay? My recommendation to students is always to limit superposition technique on to circuits when you have less than 3 power sources, because when you end up having 3 or more power sources, you basically have to solve 3 or more circuits. The way superposition works is pretty simple. You turn off all the power sources except one at a time. So let's say if I have a circuit that contains a voltage source and it also contains a current source, right? Then, and the rest of the circuit continues. So when I'm doing superposition, first of all, and the order doesn't matter, I'm going to leave, let's say, the voltage source on, and I'm going to turn off the current source. When you turn off the current source, what does that mean? Turning off a current source means that you remove it physically from the circuit, make it open circuit. then this resistor that is in the branch is irrelevant, okay? Now, conversely, if I want to keep the current source and turn the voltage source off, turning the voltage source off means that I'm going to short it, okay? Does it make sense? And it can be in a branch by itself. It can be part of a branch that contains other sources or other circuit elements. But typically, try and limit it to less than 3 power sources. Otherwise, it becomes very tricky. Mesh analysis. A couple of things that you need to remember about mesh analysis is, first of all, mesh analysis is basically just an extension of KCL or KVL. What do you guys think? Mesh analysis is an extension of KVL. So if I'm using mesh analysis to solve a circuit, there are only 2 things you need to remember. And again, this is not explicitly mentioned in the reference handbook. This is assumed knowledge. First, I need to be consistent with the direction of my loop currents. Don't set one as clockwise and the other one as counterclockwise. Please don't do that. If you're setting one as counterclockwise, set the other one as counterclockwise as well. Is that clear? Okay. The issue that students run into, a typical issue, is how to deal with this center item, right? I1, let's call it, and I2, and I have several practice problems in the course and several examples that I've solved through, right? Let's just call it R. And the way that I like to explain this is that for the center branch, the way you tackle it when you're writing your KVL, your loop, is that if I am living in loop number 1, I am going to consider loop number 1 as the dominant current. So the equation for the voltage drop across R is going to take the form of R times I1 minus I2 when I am writing the equation for loop 1. Is that clear, guys? Now, if I'm writing the equation for loop 2, the equation is going to be R times I2 minus I1. These are the only 2 things you need to understand and remember and properly apply when you're doing mesh analysis. Clear? Moving on to waveform analysis and phasor diagrams. Waveform analysis, one of the things that students routinely make mistakes is with regards to time period. Okay, time period. So when you're dealing with time period, the easiest way to identify the time period is to simply pick a spot, a milestone, a point on the graph, okay, that repeats itself again and again. Doesn't have to be this guy, right? Let's call it A. Doesn't have to be always this, or doesn't have to be always this. Okay, any point that repeats. So if I'm selecting B, then the time period I'm going to calculate is going to be between B1 and B2. This is the time period. If I end up selecting C, then I'm going to do C1 and C2. You have to pick the same point. Okay. For a graph like this, a waveform like this, sometimes students consider the time period of this waveform just to be this piece, which is incorrect. They feel like wherever you have non-zero values starting and ending, the delta between the two is the time period. That's wrong. Okay, and that can get you in trouble. Another thing that you need to really get a good handle on when you're doing waveform analysis is straight line equations, right? Now, when you deal with straight line equations in mathematics, it basically seems like a slam dunk. You are given 2 points between which you have to find straight line, or you're given a point and a slope, okay? But all of a sudden, when students have to figure out the slope of this line, for example, right, or equation for the line between points A1 and B1 in a waveform analysis problems, they actually lose their composure, right? It's not that difficult, guys. And you may have to actually come up with equations of straight line when you're doing waveform analysis. Does it make sense? Another thing to remember about waveform analysis is the average value, okay, and area under the curve and the RMS square. Okay, so if I have a waveform like this, correct, that repeats itself like this. Now, let's say this is 1, this is 2, and this is 3. Okay, and let's say this is 4. Okay, very quickly, if I ask you to calculate the average value, how are you going to do that? Can you just eyeball it? Some of you can, but my recommendation is to use the formulas that are given in the reference handbook properly. So what is the equation for average value that is given in the reference handbook? So the average value is basically, where is it? It's defined as 1 over t, 0 to t of the function. Okay. So in this case, the time period, the full time period of this waveform is actually starting from 0 to 4, right? So you have a non-zero value over here and you have a 0 value over here. So the integration that you're going to do over the time period is going to be over the entire piece over here, right? So between 0 and 2, the value is a constant, which is 3. And then between 2 and 4, the value is a 0. Okay. And then divided by the time period, which is equal to 4. The reason I bring this up is because when you're dealing with RMS values, you have to square them. So be very careful. Phasors. The two things that you need to understand about phasors is that the standard form of a phasor is always in a cosine. Okay. So if you are given a function, let's say v of t is equal to 20 times sine omega t plus 45 degrees. Okay. All right. Now, in this case, if I was to convert this particular problem into a phasor representation, right? If I want to show this as a V phasor, right? I have to write the VRMS over here and angle theta. Two things I need to be super careful with this one, right? Is the VRMS value going to be equal to 200 or something else? What will be my VRMS here, guys? The only two things you need to worry about when it comes to phasors. One is the magnitude, the other one is the phase angle. It's going to be 200 divided by square root 2, because this 200 that appears next to a sine or a cosine is a max value, Vmax. And the relationship between, so VRMS is equal to Vmax divided by square root 2. That's the first thing. Sometimes students just, copy paste 200 here or whatever the max value is. So that's the first mistake. The second mistake is assuming that whether I have a sine over here or a cosine over here doesn't really matter. It does matter. This is a sine. Okay. You need to convert the sine into a cosine. And in order to convert the sine into a cosine, you have to do the 90-degree adjustment. Okay. And what is the 90-degree adjustment? Is it a plus or a minus? When I go from a sine to a cosine, do I have to add 90 degrees or subtract 90 degrees? Do I have to add or subtract, guys? Subtract, right? If I'm not mistaken. So you are going to do cosine. So step number 1 would be, I'm going to convert this into a 200 cosine omega t plus 45 minus 90. That gives me 200 cosine omega t minus 45 degrees, right? So now when I convert this into a phasor, it becomes 200 divided by square root 2. So one possible mistake over here and a phase angle of minus 45 degrees because of this 90-degree adjustment. Okay. So these are the only couple of two items that you need to really remember for phasors. There's a question for the waveform. I don't understand the time. Yeah, so the time you just pick one, so as far as the time period is concerned, so you have 0 and 4. So this particular point repeated itself over here. So the whole time span was 4. Okay, so 1 over t shows up over here. That's where it's coming from. Okay. All right, a couple of comments regarding Thevenin and Norton. when it comes to Thevenin and Norton, setting up the circuit is super important, right? So very quickly, if I have a circuit in which the terminals are sticking out and there is no reference made to R output or R naught or RL or V naught or V output or I output, right? I don't need to remove anything, right? So this is basically a Thevenin equivalent circuit, right? Where you have a resistor in series with a voltage source with the terminals sticking out, right? And to which you can connect any type of a load, right? This is our Thevenin equivalent circuit, R Thevenin and V Thevenin, and this is RL. Now, a source transform version of this is really, and sometimes we call this R Thevenin as R equivalent. And if these terminals are open, this is going to be open circuit voltage, right? Now I have ISC over here, source current or short circuit current, and the R Thevenin or the R equivalent, right? And in terms of Norton, this is how the circuit is gonna look like, right? So when we're dealing with Thevenin and Norton, the calculation of R Thevenin, the calculation of R equivalent is always the same. There's never a difference between R Thevenin and R equivalent calculation. What we need to be careful for is, we need to be careful about is whether we need to take any resistor out of the circuit or not. The only time you're going to take any resistor out is when it is identified as our load as an output resistor. If there is no indication that a circuit within the a resistor within the circuit is an output resistor, you're just gonna go ahead and treat that entire circuit as your Thevenin equivalent circuit. Okay, through which you're gonna calculate R Thevenin and V Thevenin. Okay. When it comes to Norton, Norton tends to be a little bit more difficult for most of the students because working with the current sources and calculating the short circuit current through a shorted branch is typically challenging. All you need to do is through these terminals, you are going to introduce a short and you will calculate the current between these two terminals and call it ISC. Okay, that's the key about Norton at a high level. Source transformation, it is mentioned in the reference handbook. So if I want to calculate the source transformed equivalent circuit for my Norton, it's simply going to be the ISC value is simply going to be the VSC that you see over here, or sorry, V Thevenin that you see over there, and divided by the R equivalent. And what I'm going to do is that this R equivalent that is in series with the V Thevenin, I'm going to put that in parallel. This is a source transformation. And if you want to go from here to there, you're just going to take this ISC, multiply it with R Thevenin. You're going to call that as your V equivalent. Okay. And you're going to take this resistor, R Thevenin, and then put that in series. This is source transformation. Sometimes it comes in handy when you're doing a little bit complicated circuits. Then we have the maximum power transfer and impedance. Okay. So impedance, remember, is Z, which is equal to R plus JX. R is our resistor, the real portion of our impedance, which may or may not be imaginary. If there is reactance within the impedance, it will have an imaginary component. Okay. Now the reactance is of two types, XC and XL. Okay. So XC is called the capacitive reactance. XL is called the inductive reactance. When you go to the reference handbook, they have a very nice table, okay, where they have all three circuit elements: resistor, capacitor, inductor. The impedance of a resistor, so let's call it ZR. The impedance of a resistor is simply equal to R because there's no imaginary component, right? The impedance of a capacitor is 1 divided by j omega c. There is no resistance involved in this. And the impedance of an inductor is simply equal to j omega L, right? Then they break apart the reactance portion. So for the inductor, the reactance is basically equal to, inductive reactance is actually equal to omega L. The inductive reactance for a capacitor sometimes is a little bit tricky for students to understand because it sort of does a little bit of gymnastics with J. I've explained that in the course, but it is -1 divided by omega C. And the reactance of our resistor, we don't have any imaginary component, right? And then the reciprocals, susceptance and conductance and admittance, all of that is also defined. The maximum power transfer theorem is actually right underneath that table. I received an email from a student. Is like, okay, Wasim, you are using this equation, V Thevenin, I think it was last night, divided by 4 times R Thevenin. Where is this equation coming from? How do you derive it? Right? And I responded back that this is actually given at a face value in the reference handbook. You don't need to derive it. So what is the idea behind maximum power transfer theorem? The whole idea is that, okay, let's say if I have a black box, okay, with terminals sticking out, and it could be a very simple, straightforward circuit within the black box, or it could be a spaghetti and noodle, you know, a whole mishmash of a lot of stuff, resistors, capacitors, and whatnot. And if I want to make sure that I want maximum power to be transferred to a load, okay, RL, then how should I set up its resistance? If this is a DC circuit, how do I set up its resistance? And if it's an AC circuit, then how do I set up its impedance? Okay, the short answer is that the resistance of this load resistor should simply be equal to R Thevenin. And where's the R Thevenin coming from? From this black box. So if you can tell me what is the Thevenin resistance of this black box, and you can set or design the load resistor to have, or the load block, whatever, you can have a toy over here, you can have a motor over here, you can have whatever over here, and you can actually design or set the resistance to be equal to the Thevenin of this black box, then I will guarantee you that maximum power will be delivered to the load. That's the whole idea. And when you take this, so R Thevenin should be equal to R load. So this is for the DC setup. And for the AC setup, because you can have imaginary component as well, Z Thevenin should be equal to Z load. Actually, it should be equal to conjugate. Okay. All right. The series and parallel equivalent circuit, I already commented on that. Know how to identify series elements, right? Series elements are the ones through which the current is always constant. So same current flows through it, right? And for the parallel elements, you have them sharing the same nodes, right? So identify what a node is first. And then if both nodes of a circuit element are identical for 2 components, then they are in parallel. That's the easiest way to go about it. And there's a lot of interesting problems in terms of the quiz, mini exams, in-lecture practice problems, homework assignments within the coursework, and also the study guide where you can learn more about it. And actually that applies to pretty much all of them, right? For each one of these line items, you are going to find plenty of resources in the coursework, in the study guide, to sort of cement your understanding of these concepts in depth. One of the other comments I'm going to make, and I alluded to this earlier as well, is that if you really want to firm up your circuit analysis, then try and solve a given question using different methodologies. Okay, try and attempt it using KCL, try and attempt it using KVL, try and do Thevenin theorem on it, try and do Norton theorem on it, mesh analysis, superposition. It takes a lot of time, but the time that you invest in circuit analysis is worth it. In the long run, if you can afford to have, much time, then it's one of the few sections where your extra level of effort is going to pay off in the long run. Okay, so I hope you found this strategic review helpful, and I hope it clarifies and put things in perspective. And circuit analysis, in my opinion, you cannot overdo it. Okay, and as an electrical engineer, it is one of the most important knowledge areas and competencies that you can have, not only in the context of FE electrical and computer exam, but also for the P power exam, and also as a practicing electrical engineer in general. If you like this video, then please don't forget to subscribe to this channel. Feel free to ask me any questions in the comment section of this video below. You can find tons of success stories of my FE electrical and P power students over here. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.